Welcome back to another linear proof. In this proof, we are going to show that a matrix P is orthogonal if and only if its column vectors form an orthonormal set. And a quick little recap on what it means to be orthogonal, or what it means for a matrix to be orthogonal, is that if it is orthogonal, then that means the product of matrix P, or the transpose of P times P, is equal to the identity matrix. And so we're just going to go ahead and do a pretty much a direct proof. And we are going to start off with saying that let P be an n by n matrix such that the column vectors form an orthonormal set. Orthonormal set. And so I am going to pretty much put it in terms of like this, or let's just use capital P. P1, P2, P3, all the way to P of n. And so these are all column vectors. So these are column vectors. And if we just want to expand it through the entirety of everything, we are going to put, pretty much you write it as P11, P12, all the way to P1n, and this would be P21, all the way to P and 1. This would be P22, and this will all go to P and n, P2n, and then P and 2. And so this will be our square matrix. And so we properly defined what our matrix P is. We're already going to assume that this is an orthonormal set. And so if we calculate its transpose, we are going to get, if you recall, just the transpose, which is pretty much be switching just two values, or just switching places between the rows and columns. So this will, the main diagonal will pretty much stay the same. The transpose, or the everything else, will pretty much be P21, and this will go to P and 1. So in other words, the rows becomes the columns, P22, P12, all the way P and 2, P1n, P2n, and then P and n. And that is our transpose. So now what we're going to do is we're going to multiply the transpose with the original matrix. So if we have our pt times p, then we are essentially going to get this matrix that we just calculated. Let's see if it actually played nice, so I have to rewrite it. Paste. And then this matrix, or this original matrix. So copy, and then we're just gonna go ahead and paste. And so we're gonna multiply these two, and we can make our life simpler by, instead of doing the classic matrix multiplication, because we have the column vectors just kind of switched, so the rows become columns, we can essentially write this as the dot product of P1 and P1, P2 and P1, all the way down to Pn dotted with P1, and then this would be P1 dotted with P2, P2 dotted with itself, all the way down to Pn dotted with P2, and this will go all the way from P1 dotted with Pn, all the way down to P2 dotted with Pn, and this will be Pn dotted with itself. And so this is a dot product. So what are these dot products equal to? We don't know, because we don't know what the column vectors contain. However, we do know that the matrix P is an orthonormal set. And so what do we learn on the inner products chapter is that we learned that if given an orthonormal set, then we know two things. That the dot product of a vector in the set dotted with any other vector in that same set is equal to 0, and the dot product of a vector in that set dotted with itself is equal to 1. And lo and behold, here we have 1, 1, 2, 2, and n, and then everything else is dotted with a different type of column vector. And so what you eventually be getting is everything in the main diagonal will be equal to the unit vector, which will be 1. Everything else goes to 0. And so what do we have here? We'll have 1, 0, 0, or 1 all the way to 0. This would go to 0, to 0. This would be 1, 0, 0, and then everything across the main diagonal will be equal to 1. And what is this equal to? The identity matrix. And what does this mean? This means that P is orthogonal. And because P is orthogonal, then that means its transpose is also the inverse. Because we know for a fact that if we have a square matrix and we multiply it by its inverse, then we get the identity matrix. And because the transpose also gives us the identity matrix, then that means that the transpose is also the inverse matrix. And that's pretty much it for the proof of this video. Hopefully this made sense. Hopefully you learned something new. And I'm pretty sure this is the last proof for this lecture. This lecture. So the next video will be examples, and I'll be looking forward to doing those. So I'll be seeing you in the next video.